Today I have a story for you about a process. We are helping Caltrans to take the performance-based earthquake engineering that Pierre has built during the years into the design floor. The name of the project, Caltrans Risk-Based Seismic Design, recently changed from what it originally was, which was PDCA. I have stuff to show about the initiation, where we are, and eventually I'm going to show you how the work that we are doing in this project is going to help a Caltrans engineer or any engineer to design a bridge without the need to do many time history analysis. I'm a bit in the shock. This project gave me some heart attack this morning from putting the slides together. So starting with acknowledgements, we have been blessed with Pierre and Caltrans funding since 2008 with the list of things that I have put up there. Thank you very much. It has really helped us bring PBE to bridge engineering. Our team, which our contract manager is Sharon, we have the folks at the PDCA team, Turak, Tony, Amir, Sam, Christian, and Mark. Mark's name shows up there. And Professor Said and Nora Abramson are looking over our shoulders to make sure that what we do makes sense. The people who are working on the project is myself and the graduate student, Saurabh, who sends his regards back from Irvine. So, I don't know if the four variables for performance-based earthquake engineering, the way that it is exercised in Pierre, was showed today, but we start from the intensity measure of the ground motions to the response of the structure, and from there to the damages and decision variable. The process goes from IM to DV, which is mostly used for assessment. Bringing this to the design is a tough thing to do because engineers are really good at looking at the EDP level. Specific to this project, we had a vision from a long time ago, which the PDCA team has brought some structure to make it happen, is how we can bring this to the design floor and making it simple, that the engineer doesn't need to do nonlinear time history analysis because it's a really tough thing to do. The engineer needs to select ground motions or simulate ground motions, scaling. There's a lot of variability inside this process. And there's also importance in location and sizing, brings in variability in demand and capacity. Bringing all of this together in one package is what we have done in this project. As I mentioned earlier, the folks at the PDCA team, whose names and their paper in ASC structures is referenced here, they have a process to assess what is the EDP demand. The EDP capacity was done in a separate project, and then bringing these two together in a reliability integral, and then integrating the probability of failure over the hazard curve will give you something that an engineer can use for design. What we're looking for is designing a bridge for less than 1% probability of collapse or probability of being in a certain damage state in 75 years. Now, that is what we are trying to provide for the designers. Now, the first genius in the PDCA approach is the EDP. The response of the structure is a normalized entity called the damage index, which I have shown it here with this equation. It is how much the bridge has entered the nonlinear domain. The numerator is demand minus yield point, and the denominator is the total capacity that you have, is capacity minus yield point. And by running ground motions into bridges, we are keeping track of this parameter. That is on the demand side. If I go back into this equation for the beta, which I'm showing up here, it's not working, this guy, it has both demand and capacity parameters in it. For the capacity side, the work of Wusouri and Saidi is used, which they have collected many test results on columns, and they have come up with damage fragility curves, and they have identified 6 damage states from DS1 to DS6, which is basically close to collapse of the column. If I want to summarize what we do in this project, is that we were going to provide Caltrans with maps of demand mean and demand variability that they can inject into that reliability integral, the beta value, and find what is the probability of exceeding a damage state given the ground motion intensity measure. Once integrated over the hazard curve, you can come up with estimates, as I mentioned earlier, of what is the probability of being in the damage state or exceeding it, actually, in 75 years or any timeline that the designer is looking for. Now, throughout the rest of this presentation, I'm going to go through what is the process for PDCA and where did our work come in to reduce the amount of work. So this slide shows what the PDCA or the risk-based Caltrans design works to size a column. The engineer, for the location of the structure, for the location of the bridge, details the column. It's called the preliminary design. The preliminary design goes into a pushover analysis. Does this work? No. It goes in, well, sorry guys. The pushover analysis is done to find the capacity parameters and the yield point. Using the SDC approach, a damage index is estimated. This damage index is supposed to be, for 975 years, somewhere between 0.3 to 0.4. Let's call it the 0.35. Once we have this column, ground motions should be selected and scaled for 3 different hazard levels: 225 average return period years, 975, and 2475. Demand values are collected, which gets us to the gold spot, and then the beta equation is exercised, integrated over the hazard curve, and ultimately an estimate for what is the probability of exceeding a damage state in a certain amount of time is provided. If that is acceptable, good. Otherwise, design needs to be repeated. Our work comes and makes the gold color block easier. In order to get there, I go back to the presentation that I did last year, and we actually validated our ground motion simulation and scaling. We are using Armand Derkurian's approach for ground motion simulation, which was referenced in Zareian and co-workers and Dabbaghi and co-workers. And we are making sure that our ground motion simulation makes sense. We are using conditional ground motion models developed by Norm to make sure these ground motions are valid for the work that we do. Not only the spectral acceleration represents the hazard level, but also the PGV, which is the only parameter among ARES intensity and duration and CAV that is important for estimating demand, is validated. I'm sure that the presentations for the last year are online. You guys can look into what we have done there. The ground motion simulation and scaling method is validated for the project. This slide shows the detail of our work. We have 25-mile by 25-mile grid of California shown on the upper left corner. In certain zones, in Bay Area, Southern California, San Diego, we have done a 5-mile by 5-mile grid for each location, which in total is something in the order of 700 locations. We have a combination of these 144 column geometries. There are heights between 20 feet to 50 feet, different axial loads on the column, various longitudinal reinforcements, different diameters, and hoop spacings and specifications. All of these columns for each locations are evaluated. Only those whose damage index for design falls into between 0.2 and 0.4, which we call them viable Caltrans columns, are selected and pushed into our ground motions. The ground motions for each hazard level, we have selected 51 ground motions. There are 3 hazard levels: 225, 975, and 2,475 average return period. And the ground motion, we have selected our ground motions. The information for our ground motions are selected from the USGS recent tool 2018, which site factors and near fault factors and everything is already included in the process. So we collect the responses and we develop the damage indices. The damage indices are going to be somewhere between negative numbers because some columns don't yield, so the damage index would be a negative number, all the way to numbers above 1, going to 2.5, 4, 10. Anything that goes above 1 really doesn't make sense because our models cannot capture behavior for columns whose damage index is above 1. Below 0 gives us some numerical problem, so we club. All the damage indices below 0 are clubbed to 0, and everything above 1 is clubbed to 1. We have looked into the sensitivity of this assumption by looking into different clubbing methods. We have looked into full clubbing, half clubbing, which is only clubbing above 1s to 1, and doing a numerical integration for the reliability integral to see what difference does it make in the end product, which is probability of exceeding a damage state in 75 years. This slide shows the difference. More or less, it looks okay. The one on the blue side, the left-hand side, is basically showing what we have selected, which is probably using the full clubbing method versus the numerical integration. Again, numerical integration is the best we can do, but is not the ultimate that you can rely on. The clubbing method and the numerical integration falls really close to each other. So we have selected this approach moving forward. The first product that I am here to present to you is the map. This is the map of mean of demand damage index across California, which we have it for the 25-mile by 25-mile grid, the bigger guys, and then for the smaller regions with the 5-mile by 5-mile. All I want you guys to do is to see the trend. The trend between yellows here, which is close to 0, showing that the 225-year hazard level, not many columns yield, all the way to going to the higher and higher hazard levels. You see that more brown looks on the right-hand side. We see the difference between coastal California and inland. This is interesting, but what is more interesting, which I'm going to show in the next slide, is we are providing some fudge factors for folks, for designers, that they can use SDC, do linear pushover approach to find the demand, but using these factors to arrive at these means, because you need these means to do the reliability integral. This slide shows the variability. The variability starts also growing as we go into the higher hazard level, but ultimately you need the ratio between mean sigma and the mean to arrive at the coefficient of variation, which you used for the reliability integral beta and then all the good jazz that I showed earlier. Again, this information is a canned version of delta that the engineer can use for design of the columns, fills that golden block of the PDCA approach. Now, again, this is a slide of that fudge factor. As you can see, there's not one size fits all. There is variability in the magnification factor that the engineer needs to use depending on the location that they are for the column. Let me show this how someone can use this product. Let's say that the designer has a column with the height of, I have a hard time seeing this. The engineer wants, is it 40 feet? Yeah, it's like my glasses are a bit fogged up, I cannot see. So the designer has a column, 40 feet, 7 feet in diameter, located in San Francisco, downtown, and they want to size the hoop size and the hoop spacing. Our work is going to give the engineer the plot of this form. Horizontal axis is the transverse reinforcement ratio, and the vertical axis is probability of exceeding damage state 5 in 75 years. The information for this plot comes from a table. The table shows different hoop sizes, different hoop spacings, and the reinforcement ratio. For each point, the reliability integral, and integrating over the hazard curves happens in a simple Excel sheet whose information is coming from the maps that we are developing. So in reverse order, the designer pulls these maps, does SDC approach to find the estimate of damage index using pushover, use the fudge factor to get to the mean, the coefficient of variation comes in the canned value, betas are estimated for 3 hazard levels, integration over the hazard curve happens in the equation over here in an Excel sheet, and eventually you have this plot, which eventually they can say that what hoop size and what hoop spacing is good for their design. I'm running out of time. What we are looking at is we're going to take the work and replicate for select places using bridges rather than single columns. We're going to look into the damage fragility curves that we have and for on the capacity side and update them. And eventually we're going to arrive at some equations, we call them response prediction equations, that directly connects event parameters and some information about the structure to the EDP. And I think that is the golden item here, that you don't need to do any analysis for a preliminary design. You can directly inject that into your hazard calculation and get the DI hazard. With that, I knew that this was like 100 miles per hour. I'm happy to take questions after the finish of the session.